Hello, judges and adjudicators. Thank you for having us this afternoon. Today, our team will be sharing our proposed solution to the issue of biofouling and ways in which we can eliminate its detrimental impacts. Our team consists of 4 girls from Iona Presentation College, each with differing roles. In terms of project activities, we have distributed responsibilities into 4 categories, including planning, investigating, designing, and implementing. Hello, I am Sienna, and my role mainly lied within the research and planning stage.
I am Johanna, and I mainly undertook the designing and implementation stage.
I'm Arabella, and my role mainly consisted of the planning stage and stakeholder consideration.
I am Claudia, and my role mainly considered the design evaluation matrix and any potential constraints that our design may face.
Biofouling or biological fouling is the accumulation of microorganisms, plants, algae, or small animals on surfaces in which have a mechanical function. It is largely concerned with the growth of bacteria and algae, having an adverse impact on surrounding ecosystems and marine life. The accumulation of such bacteria creates an adhesive surface for larger organisms such as algae, mussels, and barnacles, which prompt macrofouling. The large accumulation of such bacteria and algae on marine vessels poses a significant issue.
The issue of biofouling often leads to the hydrodynamic volume of vessels and friction. According to the International Maritime Organization, IMO, biofouling leads to an increased drag of up to 60%. This increased drag has been seen to decrease speeds of around 10%, requiring an additional 40% of fuel to compensate. Not only does this pose issues for marine vehicle owners and industries, but poses detrimental issues towards carbon emissions. As a result, the IMO also predicts that concentrations of carbon dioxide and sulfur dioxide will rise between 38 and 72% by 2030. This will eventually contribute to the ecological collapses that our oceans are currently experiencing, promoting biophysical alterations such as coral bleaching events and changes towards marine food chains.
Furthermore, on how detrimental is this issue? Apart from these ecological impacts, biofouling is also known to negatively impact industries such as fisheries, underwater construction, and desalination plants. As a result, the success of these industries will likely be affected, having vast implications upon the economy. As the issue mainly affects marine structures and vessels, it is vital that a sustainable and long-term solution is implemented.
Who is directly affected? The owners of private vessels and council properties are often burdened by the issue of biofouling. Algal growth on ship hulls often leads to widespread of invasive species to various marine locations. As a result, the issue is spread relatively quickly and can soon be uncontrollable if not addressed quickly. Although our project originates in Western Australia, it has the potential to serve an extensive geographical area.
A current solution to biofouling consists of copper as a biocidal tool in order to reduce the amount of bacteria and algae growth on ship hulls. This method is implemented through the utilisation of metal ions, either alone or in complexes, to disinfect fluids and solids. Copper has often been seen to purify drinking water, having various antifouling and bacteriostatic properties. As such, this paint significantly reduces the concentration of unwanted bacteria and algal growth.
A relatively common method of anti-biofouling consists of the use of medetomidine to remove barnacle settlements on the hulls of ships. The medetomidine substance is regularly placed within affected areas and is able to create a toxic surface, being able to kill the larva. It is also able to avoid attachment and settlement on a surface. However, this current solution is relatively time-consuming and expensive. Although being effective in the removal of barnacles and algae, it requires regular application of the substance, which can require much more time and be highly inconvenient.
The typical biofouling process has 5 stages. The first being bacterial cells will settle onto the hard surface. The cells will then proliferate and secrete slime, forming a biofilm. Some cells will detach and the protists graze on bacteria. If enough biofilm forms, large organisms can attach to it.
After considering various solutions, we have devised a sodium alginate jelly substance which adheres to our economic and environmental goals. This solution is aimed at removing any bacterial substances whilst not posing any threat to any external marine life. When placed on the affected surface, the jelly creates a vacuum seal, limiting the amount of oxygen that is available to the bacterial growth. Not only is this solution effective, but differs from existing biofouling solutions that may not be accessible to a wide range of people. Its ingredients are only targeted towards bacteria and algae, having no effects on outer marine life. In terms of its adaptability and scalability, the solution is relatively subtle and does not take up too much space. It is easily applicable and does not require any expensive machinery to remove.
Sodium alginate jelly does not take up a large amount of space. It can merely be applied to the affected surface without any advanced machinery, as mentioned previously. It is a clear, adhesive substance that is able to sustain long periods of time in both fresh and salt water. In comparison to copper biocide and biomimetic coating, the sodium alginate jelly can easily be applied without any harm to the user or the environment. After considering various solutions, we have chosen our sodium alginate jelly using a design evaluation matrix which analysed a total of 3 possible solutions. The 2 other potential designs included copper biocide and biomimetic antifouling coating. Each possible solution was scored using a value between 1 to 10, with 10 being the most viable. We analysed a total of 8 factors, including cost, safety, lifespan, footprint, adaptability and scalability, environmental impacts, testability, and innovation.
We added in the factor of testability due to the fact it determines whether we, especially as students, will be able to test it and use it as a solution. We also added innovation as a factor because we are an engineering class trying to look for new solutions that work better than existing solutions. We also prioritize environmental impacts and safety because our team wants to ensure that we aren't causing the death of our own world to come at a faster rate. We also changed the weighting of some of the criteria, figuring that some would have the ability to override the others. These were the environmental and safety criteria, as they are considered to be the most important factors.
A sustainable approach. Our solution considers the 3 factors of sustainability: social, economic, and environmental. These factors are indivisible and exist independently. It ultimately ensures that the solution considers a reasonable cost, is ethical, and ensures that surrounding marine life are not impacted. In terms of economic factors, our solution must be affordable for the general public and easily applicable, ensuring that the issue can be addressed on a global scale.
How it works. Our sodium alginate solution includes the ingredients of sodium alginate, barley straw, and gelatin. Barley straw is known to slowly kill algae naturally as it rots. It is mainly effective when exposed to a body of water. Unlike sodium alginate, barley straw does not kill existing algae, but inhibits the growth of new algae. This, in conjunction with the sodium alginate jelly, will ensure that there is limited oxygen available, thus causing the algae to slowly die.
Contrary to popular belief, barley straw does not reduce the growth of other aquatic plants and is in fact safe for all marine life. According to some previous cases, it has actually been reported that some aquatic plants have experienced much growth after barley straw applications due to there being no algae left to compete with.
During our first testing round, we attempted to make the jelly without the use of sodium alginate in order to achieve our desired consistency. This was also due to the absence of sodium alginate as an integral ingredient. The first part of our testing procedure involved boiling 150 milliliters of water with a small quantity of gelatin and barley solution. Once the solution reached boiling point, we transported it to a refrigerator where it would gain its jelly consistency. However, after analyzing our results, we found that we added too much water to the solution, causing it to lack its jelly-like consistency. It was also left in the fridge at too low of a temperature for an extended period of time. This, in conjunction with an excess amount of water, caused the solution to freeze and lack its adhesivity. Once it melted, it formed a jelly-like material, but continued to lack our desired consistency. Due to adding too much water, the solution was liquefied and did not possess the thickened material that we desired.
Our second testing round was mainly aimed at improving the consistency of the solution, ultimately ensuring that it is adhesive. During our second testing round, we used a larger quantity of gelatine and less water. After analysing our results, we found that the consistency of our solution was significantly improved and possessed a thickened jelly consistency. We also placed the nails in the jelly before placing the solution in the fridge in order to assist with its adhesion. However, once taking it out of the fridge, we continued to find that the solution was frozen again, which largely impacted its functionality. On the other hand, during our third testing round, we followed a similar method to our second testing round. However, this time we added 300 millilitres of water whilst doubling the gelatine quantity. This would ensure that the nails would be surrounded by a thickened amount of jelly. As opposed to putting our solution in the fridge, we left it at room temperature in order to prevent it from freezing and losing its consistency. We found that this method was the most successful, having obtained our final desired consistency and quantity. Yeah, so as you can see, we have used, we've actually placed jelly, which contains a nail in order to maybe replicate the structures of maybe ship hulls or port structures. And this contains water, whilst the other ones don't contain anything, just for a representation of what they look like.
This one we had used string in order to make sure the entire nail was covered in the sodium alginate to see how we could implement string and things to make sure the entire thing is coated.
Our finalized solution, after conducting various testing rounds, we have finally reached our desired consistency. Having tested the solution in both fresh water and salt water, after actively testing our solution in water, the solution's jelly-like consistency was not affected by the water. We used nails in order to somewhat replicate the material of port structures and the hulls of ships. When faced with water, the jelly was able to contain the nail and was secure.
Why our solution will be a success. It considers all areas of sustainability. The solution is safe for both marine life and the applier. It does not require heavy machinery. It supports existing aquatic life while inhibiting the growth of algae. It reduces concentrations in carbon in the oceans.
One of our prevalent stakeholders consists of council properties. These stakeholders are largely motivated by the ability to have clean ports and ultimately reduce biofouling on their properties. Although we do not particularly need any raw materials from them, having them as a customer of our product would be greatly beneficial. Once we have gained their trust, they will serve as a fundamental stakeholder, majorly influencing the success of our solution. Government-owned marine vessels also are a prevalent stakeholder of ours. From submarines to large army ships, the government requires the use of many marine vehicles which will need protection from biofouling. They likely desire an effective but also support affordable solution from a trusted source. Once again, we do not need any raw materials from them, but they would be a vital customer and a prevalent source of funding for our solution.
Another stakeholder would be the Australian shipping sector. Various marine vessels and ports that are involved in this process are largely affected by the accumulation of bacterial and algal growth. Not only does this have a vast environmental effect, but negatively impacts the efficiency of this major sector. Shipping agents are key stakeholders, linking the international shipping community to government requirements. State governments may be interested in funding our solution, as biofouling may pose adverse effects on this vital industry. Businesses and industries, whether they are privately owned businesses or mass industries such as fish farming, we found that a significant stakeholder for our anti-fouling solution would be within the business sector. Various companies such as fisheries greatly depend on their marine vessels in order to source their products and ultimately achieve a profit. Although these stakeholders would not fund our project, they would benefit greatly from a convenient and simple biofouling solution. This stakeholder will likely be a large supporter of our method of solution.
In conclusion, after analysing the issue of biofouling and its detrimental impacts, we found that our sodium alginate solution is likely to benefit a range of individual and government marine vessels. Due to combining a sustainable approach with a range of economic, environmental, and social factors, we hope to adhere to our target population and potential stakeholders. By combining sodium alginate solution and barley straw to form a jelly-like substance, we hope to provide a unique and innovative solution. Our ultimate hope is to be able to effectively combat this widespread issue.
Thank you. And if there are any questions, feel free to ask.
Thank you so much, girls. Round of applause. I'd like
Thank
to answer your question. Jitendra, first up.
Okay, can you hear me?
Yes, yes.
Okay, imagine having jelly-coated ship, okay, and it goes into the sea, and the waves shear off all the jelly, right?
Yep.
Have you thought of your future work involve kind of a stream-like simulation and putting these nails and see how much the alginate adheres for some time?
Yep.
Alginate is used in microbiological and industrial applications for immobilizing cells, and it only becomes a solid thing if it is actually mixed with a salt solution which is inert. So I would recommend that you actually have some kind of a simulation where you put these nails stationary and have a running water and see how long it lasts. Have you thought of that?
Yeah, that definitely is a good point because although we have used nails to replicate maybe the hulls of ships or port structures, it definitely could serve as future work to maybe form a simulation for like running water. We have practiced moving our solution containing nail in and out of water, but we found that we should definitely maybe find more of an active simulation to serve as like a true representation of the actual like ocean.
Yeah.
Okay, thank you.
Thank you. Any other questions?